Good morning. Let's get started. We discussed the motivation for fully differential circuits and systems. Basically, they are less susceptible to interference, and they also put out less interference. That was the idea. So every signal is represented using two wires which are swinging in equal and opposite manner. We also looked at how to analyze these circuits. You can use differential and common mode half circuits to analyze them. It is best to work them with an example. So the sort of classic example is a differential pair with a symmetric load, right? So this is something you are very familiar with. These are the two inputs and these are the two outputs. Okay. So now the input can be represented as the input common mode plus and minus half the differential component. Similarly, the output can be represented as VOCM. I have defined this side to be VOM. That's why I put minus. It doesn't matter which way you put it. You will always, of course, get the right answer. Output common mode plus minus half the differential component. Okay. So now we can do half circuit analysis with this, right? So this is the fully differential circuit, and then if I first consider the common mode half circuit, what do I mean by that? I have only the common mode part of the signals. Okay. That is basically how it is, right? So now we know just by inspection that the two sides obviously have the same solution. In fact, in this case, I have marked all of them. So you can just tie the corresponding nodes together. Actually, there is only one particular node here to tie, one pair of nodes, right? This one, that's all. So you would tie these two together and do the analysis. If you wanted to sort of formally do the common mode half circuit, what you would do is you replace this with half M naught for the sake of analysis. Okay. Two of them, right? And then if you draw this center line, the line of symmetry, you know that on any wire crossing that line of symmetry, what happens in the common mode half circuit, in the common mode picture? Currents, there is no current crossing that line of symmetry. So you can just cut it off and do the analysis of only the half circuit, which would be with M1 half of M0. Okay. So now, I mean, this is not at all complicated. So the current here will be I naught. If this was 2 I naught, the current there would be I naught. So the operating point voltage VOCM, what would that be? VDD minus I naught RL. Okay. Similarly, this tail voltage would be VICM minus VGS1 at a current of I naught. Okay. So essentially, you solve the common mode half circuit, and then you use the same solution on the two sides, because you know that the solution will be the same. Okay. This is a relatively trivial example, but basically this is the idea. The only thing to keep in mind is there may be components like this which apparently are not in two halves, but I mean you can always split that into two components. If you have a conductance, you have two half conductances in parallel. If you have two capacitances, you have two capacitances of half the value in parallel, and so on. So you can always split that into two parallel halves and then assign one to each half. Is this okay? So this is a relatively trivial example. Now, like I said, the common mode half circuit is valid even for the operating point, because it's valid even for nonlinear circuits. Okay. Now, the differential half circuit, on the other hand, in case of differential, we assume that we have only the differential excitation, and this of course is valid only for the small signal incremental case, because we are using the half circuit will be first of all we evaluated at the operating point, and it uses linearity to say that the nodes along the center line will have 0 voltage. Okay. So I will still write the transistor symbols, but basically now if you draw the center line, this is at 0 volts and that is at 0 volt. Okay. So the differential half circuit would be the excitation is VID by 2, and on this it is minus VOD by 2. I mean, that's how I have taken that, right? This is M1. So what is the gain from here to there of this circuit? This you can tell by inspection, right? What circuit is it? It's a common source amplifier. So this is the differential half circuit. Okay. And we know that minus VOD by 2 divided by VID by 2. This is, how much is that? Minus GMRL. So VOD by VID, which is our VID is like this between these two, VOD is between those two, VOP minus VOM. Okay. So how much is that? That is GMRL. Okay. This is fine, and it comes out to be positive. That's because of the way VOP and VOM are defined, right? So this is fine. This is how you would do the half circuit analysis. Is this okay? Any questions? Now let me take maybe a slightly more complicated case. So let us say that I have these resistors, and there was a question about cross coupled components. I have these also. Okay. I have RL and I have M3, M4. Let's assume that there is enough voltage across the source gate to keep them on, right? To have them to be on. Is that okay? So now how would you go about doing this? Please draw the common mode and differential half circuits first of this one. Please draw the differential common mode half circuit and the differential half circuit. But anyway, so many of you have got it right. First of all, if you in the common mode picture, this is what you have. Okay, I think I should have copied it with the transistors. So let's see. So the point is this and this are both at VOCM. Okay. So basically, the gate of this MOS transistor and the drain are at the same voltage in common mode. Okay. So the correct common mode half circuit would be diode connected transistor, and then you have M1, this is M3, RL, and half of M0. Okay. From this, you can calculate the operating point. It may be slightly messy, but basically, this current essentially, if this voltage is denoted VOCM, you have to now make the sum of these two currents, current through M3 and current through RL equals I0. Okay, that will give you VOCM. It may be a slightly messy thing to calculate, but that's how you calculate it. Okay. So this is the common mode half circuit. Just a minute. Both are at VOCM, right? This is at VOCM, that is at VOCM. They are at the same voltage, right? It doesn't matter. So that basically, when you solve for the currents, you should get the same answer. That's all. Okay. Or I mean, if you think of in the common mode picture, you can fold the two sides, two halves on top of each other. If you do that, they'll get diode connected anyway, right? Both will get diode connected. Okay. So now in the differential picture, what do we have? So now, which are the nodes along the line of symmetry? How many such nodes do we have? It's actually only this one, right? So these, they are not connected to corresponding nodes, right? So this is at 0, this will be at 0, these will not be at 0. Okay, this one, for instance, the gate of this is connected to the drain of this and vice versa. Okay, it's not that these two will be at 0. Okay, so you see that, for instance, this voltage, this is at minus VOD by 2, and the gate of this M3 is at plus VOD by 2. Okay. So the correct differential half circuit is you have RL. This is of course at 0. This is minus VOD by 2, and we have the usual M1, and its source is at ground. And you will have M3 here, and this gate will be at plus VOD by 2. Okay. So this is how it is. So now, if I have VID by 2 here, what is the current there? Let's neglect, let's say, the GDSs. What is the current there? What will be the current? GM1 times VID by 2. What is the current here? What is the current over there? This is M3, let's say. What is that current? GM3 VOD by 2. What is the current there? Minus VOD by 2RL. Okay. So now we have GM1 VID by 2 plus GM3 VOD by 2 minus VOD by 2RL to be 0. Okay. So what is VOD by VID? It is GM1 by GL minus GM3. GL is basically 1 by RL, right? So if you make GM3 equals GL, what happens? You get infinite gain. You may not be able to make it exactly equal, but basically that's one way of increasing the gain. Okay. So essentially this cross-coupled pair, right? It behaves like a negative resistance. I'll show this. In fact, the assignment had things like this, right? You were asked to calculate the impedance. I don't know if the cross-coupled one was part of it. Was it there? Yeah. So you must have got the negative resistance as that value. Okay. So essentially, you have a positive conductance GL and a negative conductance GM3 across it. So the conductance actually decreases by putting a positive and negative conductance in parallel, or you can make it decrease. So that's one way to enhance the gain. Okay. So this is the, I mean, right now we are only discussing common mode and differential half circuits, but the purpose of later we'll see what is called as common mode feedback is to reduce the common mode gain and enhance the differential gain. Okay. Yeah. Right. No. Which side? Where is the capacitance? Right. So, but it is still symmetrical. That is, this has some CGS and then some CDB, right? And this also has some CGS and some CDB. Okay. So, these two will be part of the differential half circuit, right? Well, actually, that's a good question. So, let us see. Huh? Yeah. You should not CDB by 2. Let me see. Actually, this is a tricky situation because finally what comes out in the answer is CDB plus CGS, right? So, yeah, I think all the impedances should be transferred to one side. Only the control should be passing from one side to the other. I think that is what it looks like. So, because if you put, for instance, now if we have only CDB here and CGS there, okay, then the parasitic pole will come out to be wrong. Okay, because the parasitic pole should have CDB plus CGS. So basically, what you can have are, I mean, when you have this cross coupled stuff, it's a little tricky, but only, I mean, if you put this in parallel here and that one in parallel there, it works. Okay. So let me think about it a little further. Maybe there is some other way of making it work also, but good question. Yeah. No, we can, but the question is, I mean, if we are going by the algorithm, why is the other one wrong? That is, I just split it like this and retain only whatever is on this side. Okay. So that appears to be not correct. I mean, that appears to be not incorrect according to whatever I've been describing, but that will give the wrong answer. So I have to think a little bit about what exactly is happening. Okay. Whereas if you do add it, if you do add this one here and that one there, the answer will come out to be correct. That is for sure. Okay. But on the other hand, why put this one here? I could put this one there and that one there, then there will be no capacitance at all. So there will be no pole. So obviously, like all of these cannot be correct. Okay. So let me think about what the conditions are. If there's any. Yeah, if you have corresponding ones, I mean, then uh, no. I mean, if you have only the corresponding nodes connected, right? The nodes along the line of symmetry will have 0 voltage. So any parasitic capacitance from that node will have no effect in the differential picture. In the common mode, yeah, in the common mode, they will not be separated anyway. That is okay. I don't think this, there is no problem here with the common mode. The common mode comes out correct because however you split it, you will have a capacitance there and a capacitance there. Okay, whichever way you move it, as long as you move it properly to the two sides. The problem is only in the differential picture where we have this coupling. Okay. So I have to think about a little more about what happens. Any other question? So now, before we go further, So here, let's say this is 2I naught, VICM, VICM plus VD by 2 minus VD by 2. What is the differential output? It will be GM1 RL VD. Okay. Now let's say I have this. And here I use some V bias so that the current is I naught and there is I naught. Okay. The voltage there that way, the output voltage. What will it be? The operating points I have chosen to be the same. So what will that voltage be? Same as earlier, right? It will be, I mean, it will always be GM1 RL VD and GM1 is the same as before. Okay. What is the difference between these two circuits? I mean, what are we gaining from this extra transistor at the bottom in the first circuit? They seem to give you the same output, right? What is the difference? Common mode. What is the difference in the common mode? Very different bias. Well defined. The other one also has well defined bias. No, I choose the value V bias, that's all. Yeah. So this is not very, I mean, both are fully symmetric circuits. What is the same? The differential half circuit is the same. This for both of them, right? But what about the common mode half circuit? What is the common mode half circuit of this? What is the common mode half circuit of the other one? What's the common mode half circuit of this? Same as the differential half circuit, right? Now, what kind of circuit is this? If you, let's say this is small signal VCM, you can think of it as M1 degenerated by some very high resistance. In fact, if this current source is ideal, the gain is 0. The common mode gain is 0. Whereas here, what is the common mode gain? This will be minus GMRL VCM. Okay. So the common mode gain is the same as the differential gain. Okay. In fact, this differential pair is, I would say, the only circuit that inherently gives you common mode rejection. That is, because of this tail current source, what is the tail current source doing? If the tail current source is ideal, it is keeping the sum of the two sides to be constant. What does it mean for the sum of the two to be constant? That means that the common mode current is not varying, right? In other words, if one of the currents, if the current in through M1 varies in some direction, current through M2 must vary in the opposite direction by the same amount. So it is enforcing a differential behavior. Okay. So the differential pair is the only circuit that has common mode rejection by itself. Okay. So in this case, the load is the same in the differential and common mode halves. Okay. Whereas this one has common mode rejection, this one does not. This has 0 common mode rejection. 0 means 0 dB common mode rejection. Now common mode gain and the differential gain are the exactly the same. So you cannot use this as an op amp. Okay. So you can't use that as an op amp. Whereas you can use this because it has no common mode rejection. You know that you have to have common mode rejection in the op amp, right? Now, of course, there are you will use blocks like this and you may want to increase, you may want to have some common mode rejection. So this is where the problems of the circuits of the type you saw in the assignment come in. Okay. So the differential FIRE has its common mode rejection, but let's say we were operating in a case where the amplifier part has no common mode rejection at all. It treats differential and common mode circuits equally. What you can have instead are load structures which behave differently for differential and common mode. Okay. So one particular example is the following. So let us say that so let's say M1, M2, M3, M4, M5, M6. That is with differential inputs, and then with common mode inputs you would have okay. Now please evaluate the differential and common mode gains for this by drawing the half circuits. Okay. So what I suggest you do is the NMOS transistors you model you only using GM. The PMOS transistors have both GM and GDS. Okay, and let's assume that M3, M4, M5, M6 are all identical. Okay, for simplicity. So please evaluate, please draw the differential and common mode half circuits and evaluate the differential and common mode gains. So what do you get? In the common mode picture, in the common mode half circuit, you would have M1 VICM, and essentially these will get shorted together, right? So you would have M3 like that, 5 like this. In fact, this also helps point correctly. Okay. So now in the small signal picture, if you evaluate this VOCM by VACM, it would be minus GM1 by the sum of these GMs plus the sum of GDSs. If you assume they are the same, it will be okay. In the differential half circuit, what do you get? You have M1 VID, and then you have this diode connected transistor and another transistor. Okay. Now, if you evaluate this, what happens is you have the GMs of these two transistors and they'll be carrying equal and opposite currents. So they'll just get cancelled out. You have GDSs of these two transistors, they'll appear in parallel. Okay. So if you have not yet work it out yourselves. So this is VID by 2. So POD by VID will turn out to be GM1 by 2 times GDS3. Okay. So you will get a differential gain that is much higher than the common mode gain. Okay. So this structure, in this case, the common mode rejection is coming from only from the load, not from these. This part is indiscriminate. It will amplify common mode and differential signals equally. Okay. What is differentiating the common mode and differential mode is the load. Okay. So we will again, I have not defined what is common mode feedback yet. We will have common mode feedback structures. Basically, the idea is to present a small common mode impedance and a large differential mode impedance. Okay. Now, in general, you know, how do you make amplifiers? You make currents flow through impedances. To have high gains, you should have currents flowing through very high impedances. Now, this should happen for the differential picture. For common mode, in fact, ideally, you don't want the common mode to vary at all. So that means that common mode impedances should be 0, a short circuit. Of course, you will not get 0, you will get some low value. Okay. So now, if I take this for instance, and use a differential pair here, what happens? What happens in this case? So you will have common mode rejection from both the bottom structure, the differential pair, as well as the load. Okay. So the common mode gain would be what? The common mode half circuit, what is the load impedance? We just saw that, right? It is basically 1 by 2 GM3 plus GDS3. That is the load impedance in the common mode half. What will be the GM4 common mode signals of the bottom side? Yeah. So it will be approximately 1 by 2 RDS0, right? Because I mean, assuming it's a degenerated differential pair. Immediately see this, write it out and see. It will be GM1 by 1 plus 2 GM1 RD as 0 and this will be much greater than 1. That's the approximation I have made. So now the common mode gain is even lower than before, and the differential gain, what is it? What will it be? It will be GM1 by 2 GDS 3. So the ratio of the two will be even higher than before. It will be the common mode rejection of the differential pair times the common mode rejection offered by the load. Okay. Is this fine? Any questions? There are many ways of setting the common mode. I'll discuss the general technique, but there are many specific circuit techniques as well, which are quite useful. Is the idea clear? So now we will make fully differential circuits, of course. Fully differential circuits we can analyze using common mode and differential half circuits. And the idea behind having you get the advantages of fully differential circuits only if the two sides are varying in equal and opposite manner. So that means everywhere you should have differential signals, but no common mode signals. Of course, it's not possible to have zero common mode signals. You should like to have it to be as small as possible. So that means that you should have common mode rejection somewhere. If you don't have common mode rejection anywhere, then this business of using two wires for each signal may or may not make any difference. The idea is finally you are sensing the difference voltage between the two wires. That really means that that's another way of saying you have common mode rejection. Okay, because you're only sensitive to the different signal and not the individual signals. Okay. So now with this, let's go to our op amps. Let's go to the single stage op amp. What was the idea behind the single stage op amp? You have a differential pair with an active load. Okay. So now you will have the same. Only thing is earlier you were taking the output only on one side. So we used a current mirror as a load. So now what we need is a fully symmetric structure. Right? And then how do we bias that? First, let's assume that it is biased correctly. Okay. It is biased so that all transistors are in the saturation region. What is the differential gain of this? What will be the differential half circuit? Differential half circuit would be M1 connected up like that, and then M3, this will be connected to ground. So what will be the gain from here to there? It will be minus GM1 by GDS1 plus GDS3. Okay. What is this? This is the gain of the single stage op amp, right? As you expect. So that way this will work. But of course, you have to set the operating point correctly. Okay. So that means that this voltage, because if you just make this, there is no guarantee. I mean, if this tends to carry a higher current, then these voltages will keep going up until M3 and M4 go into the triode region. If they tend to carry a lesser current, then this will keep falling until M0, M1 and M2 will fall into the triode region. Okay. So now we need to adjust the gate of M3 and M4. So this is VG34. such that this voltage reaches some desired value. Okay. How do we do that? So first is, when we are looking at the operating point, it is by definition common mode. It is the same for the two sides. So we can just look at the common mode half circuit of this. Okay. Right. And we want VD1 to have some definite known value so that all the transistors remain in the saturation region. And the way to do that is by adjusting this VG3 or VG34. Okay. So how do we do this? How do we make sure that what are all the different ways you can think of? This looks like a simpler problem, right? Basically, whatever current is flowing here, I naught, the other side should supply exactly the same current. Okay. And in the process, to adjust VD1 to some definite value. So what are all the different ways of doing this? Feedback. Okay. So specific realizations. So many possibilities, right? So the simplest thing may be just like biasing. You think of now just biasing M3 at the right current. You can do that. Okay. By the way, this is not complete. This is just, this will take care of the common mode. Now then you have to marry the differential picture with the common mode picture, right? So that in the differential picture, you should get this so that you have a high gain. And in the common mode picture, you get whatever you have to, so that you have a biasing point. What else can you do? You know that you can pass it through any stage that has a positive incremental gain, and it will work in the same way. Of course, you have to make sure that VD1 attains the right value. And if you want VD1 to be at some known fixed value, let's say 1 volt, how will you do it? What will you do? So you may have to do something like this. You compare it to that whatever it is, let's say 1 volt, or let me call it VCM ref, whatever reference voltage you want to have, and then complete the loop, and from the polarity of the feedback, you know it should be like that. Okay. So any of these circuits will work, and we will use all of them, right? Depending on the context, some are maybe more suitable than the others. Okay. Yeah. For what is that? Yeah. Okay. No. We don't know what the VCM we want. We have not defined. Right now, it is enough if all transistors remain in the saturation region. Okay. So any circuit that makes that will be fine. And then, of course, the circuit we follow this up with may put some more constraints on VD1. But right now, I mean, if we do this, what will be the VG3? It will be VDD minus VSG of that. Okay. And because this is diode connected, and of course, assuming VICM is sufficiently low, this will for sure keep all the transistors in the saturation region, right? So that will work. Okay. So now please think about how to combine these with the differential circuit. And what is the principle to use? So again, in the differential half circuit, whatever the line of symmetry will be at 0 volts and so on. Okay. So that is what you would have to use to combine these. This is somewhat similar to earlier we had different biasing techniques. We have different amplifier functionalities, the incremental pictures, and you combine the two using some things. Of course, we were using AC coupling heavily probably at that time. Now we won't use that. Okay. Please think about that.